In this video, we're going to look at our inverse trig functions or inverse circular functions. Now, we have used inverse trig functions a little bit earlier in the course when we were just trying to find the unknown angle from a basic trigonometric equation. But we're going to get a little bit more into these functions to better understand really what our calculator was giving us in the first place. So let's do a quick review just of inverse functions from perhaps a college algebra course that you might have taken. So if we're given an equation in two variables, say x and y, to find the inverse, we switch x and y and then we solve for y. If we're given a relation, so a mapping of some sort or a table of values, we switch the inputs and the outputs, and that gives us our inverse. And given a graph, we switch the coordinates of each ordered pair, or we can reflect it over the line y equals x. So these are all techniques that we use to find inverses previously. So let's think about how this relates to sine of x. So we're going to look at the equation y equals sine of x, and we're going to use that table of values we used to graph this function previously in a previous unit. So we used x equals 0, x equals pi over 2, x equals pi, x equals 3 pi over 2, and x equals 2 pi. Those were those landmark points that we used. Sine of 0 is 0, sine of 1/2 is 1, or sorry, sine of pi over 2 is 1. Sine of pi is 0, sine of 3 pi over 2 is -1, sine of 2 pi is 0. And we can use these we can use these landmark points to graph this function. So this is just a quick review of graphing this function. We've practiced this a lot up to this point. So sine of 0 was 0, sine of pi over 2 was 1, sine of pi was 0, sine of 3 pi over 2 is -1, sine of 2 pi is 0. And if we were to look at this, we know that this pattern does continue. So while I only plotted those 5 points, I do know the behavior will continue to repeat itself. Now, if we were to switch these and we think about even just the table of values, so the x and the y values, or the inputs and the outputs, are going to swap sides of that table. And this is going to give me my inputs and my outputs of my inverse. So instead of the x values being the 0 pi over 2 pi, 3 pi over 2, 2 pi, now they're the 0, 1, 0, -1, 0. And the outputs are 0, pi over 2, pi, 3 pi over 2, and 2 pi. So if we were to graph these points, now our x coordinates basically go from -1, 0 to 1. And our outputs go from 0 to 2 pi. So we have 0, 0 as a point. Then we have 1 and pi over 2. So that's going to be a point in that first quadrant. Then we have another point, 0 pi. Then -1, 3 pi over 2. Then 0, 2 pi. So if we start connecting those points, and it should be a little bit more curved, but it's harder to do that. What we notice is that even if this weren't to continue, this graph now fails the vertical line test. So it's no longer a function. Because it fails the vertical line test, what we're going to do is we're going to restrict the domain of sine of x, which would then restrict the range of inverse sine of x, so that we do end up having a graph that passes the vertical line test. So we're going to restrict the domain from negative pi over 2 from here to here. And if I think about what part of the graph that looks like, that's going to look at just this section, which then also looks at just this section on that graph of the inverse. Or actually, rather, if we were to continue, it would be this part of the graph of the inverse. Now, because of that periodic nature, we could look at different intervals for this, but we default to these intervals, and these are the intervals that our calculators operate on as well. So with all this said, let's summarize our inverse functions for sine, cosine, and tangent. Y equals sine inverse of x, and we use that exponent of -1 to denote an inverse. And we can also write this as arcsine of x. This is another notation for an inverse trig function. You'll see both of them, be familiar with both of them. The domain of our inverse is going to be from -1 to 1. And our range is going to be negative pi over 2 to pi over 2. Now, again, thinking about that review of inverse functions that we did at the beginning, since we're switching x and y, we are switching our domain and our range. So this range of negative pi over 2 to pi over 2 is the same as the domain, that restricted domain for sine of x. Now, if we think about the graph of this, which we won't use the graph that frequently, but we can see visually, here's our grid set up from -1 to 1 on the x-axis and negative pi over 2 to pi over 2 on the y-axis. And we have this truncated S-curve going through the points -1, negative pi over 2, 0, 0, and 1 pi over 2. But what I want to focus on is the range here. What this means is that if I were to plug in something into our inverse sine function, the output, which is going to be an angle, we use our inverse trig functions to evaluate or find an unknown angle. That angle is going to be between negative pi over 2 and pi over 2. So if we think about this in terms of the unit circle, this sine function is going to give our inverse sine function is going to give us an angle in either quadrant 4 or quadrant 1. And this last piece of information is really what we're going to use when we're implementing our inverse trig functions to solve things like trig equations, which we'll see in a little while. Understanding what that inverse trig function output gives us can help us identify what the solutions or the actual angles that we're looking for could be. Y equals inverse cosine of x. Again, we can use the notation of that -1 exponent or arc cosine now. The domain for our inverse cosine function is -1 to 1. And the range is going to be 0 to pi. Again, we're restricting the domain on our y equals cosine function so that we do end up passing the vertical line test when we look at the inverse. And that range of 0 to pi is the restricted domain of y equals cosine of x. So setting up my grid, my x-axis goes from -1 to 1. My y-axis is going to go from, we're going to look at from 0 to pi. Cosine inverse of -1 is going to be pi. Cosine of 0, or cosine inverse of 0 is pi over 2, and cosine inverse of 1 is 0. So again, we're going to see just that truncated S shape, which is going to be part of that reflected cosine function. Thinking again about the output of our inverse cosine function, that output is going to be a value between 0 and pi, which if we're thinking about the unit circle, that's going to be Q1 and Q2. So anytime we plug in a value into our inverse cosine function, the output's always going to be a number, an angle in quadrant 1 or quadrant 2. Now, that doesn't necessarily mean that's the angle we're looking for. So we're going to have to use some problem solving techniques, but understanding what the inverse trig functions give us, what values they could be, and how it relates to the problem we're solving is going to be very important. Y equals inverse tangent of x or arctangent of x. The domain for inverse tangent is -infinity to infinity. And the range is going to be pi over 2 to pi, sorry, negative pi over 2 to pi over 2. And I didn't emphasize this before, I should be more careful. The range for inverse tangent is negative pi over 2 to pi over 2, but we're not including either of those endpoints. Alternatively, the range for inverse sine and inverse cosine are both inclusive intervals. So we are including both negative pi over 2 and pi over 2 in the range of inverse sine, and both 0 and pi for the range of inverse cosine. Now, if we think about the graph of tangent x, we had vertical asymptotes at negative pi over 2 and pi over 2. Now we're going to have horizontal asymptotes at y equals pi over 2 and y equals negative pi over 2. Which is why those two endpoints in the range are not included, because now they've become horizontal asymptotes. Inverse tangent of -1 is going to be negative pi over 4. Inverse tangent of 0 is 0. Inverse tangent of 1 is going to be pi over 4. So we have a graph that looks very similar to what a cube root function would look like, bounded between two horizontal asymptotes. In terms of the unit circle, again, since the output of inverse tangent is going to be between negative pi over 2 and pi over 2, that output is going to be either an angle in Q4 or in Q1. All right, so let's utilize these inverse trig functions a little bit more. Find the exact value for the following. Again, highlighting that direction of finding an exact value means you would not be grabbing your calculator. So y equals sine inverse of 0. We're trying to figure out, what does y equal? Before I go into this, I do want to add, I have a note here. Assume in these problems that we're measuring in radians unless otherwise stated. So unless they ask you for that angle or the inverse trig function value in terms of degrees, always yield or assume to give that value in radians. So y equals sine inverse of 0. What we want to think about is sine of what angle has an output of 0. So again, our inverse trig functions, they help us figure out an unknown angle. So we're trying to figure out the angle y such that sine of y is equal to 0. But we also know that our inverse sine function only gives an output between negative pi over 2 and pi over 2. So we're trying to figure out where sine of y equals 0 in the interval from negative pi over 2 to pi over 2. So I'm thinking visually, my unit circle Q4, Q1, where do we have sine of equal to 0? That's going to be at x or at 0. So our y value here is 0. Y equals cosine inverse of -1. So again, we're thinking cosine of y is equal to -1. So where does cosine equal -1? But that's on a specific interval, the interval from 0 to pi. So thinking about my unit circle in the first and second quadrants, where do I have cosine equals -1? That's going to be at pi. Y equals arctan -1. So where does tangent of y equal -1? On the interval from negative pi over 2 to pi over 2. We're not including those endpoints though, because those are going to be asymptotes. Well, we know tangent is that ratio of sine over cosine. So if that ratio equals positive or -1, it's got to be at one of those pi over 4 units. Since that ratio is -1, we want to be in the fourth quadrant, or y is equal to negative pi over 4. Which is coterminal. If we think about the unit circle, negative pi over 4 is coterminal to 7 pi over 4. But again, thinking about the range that we have for our inverse tangent function, the range is from negative pi over 2 to pi over 2. So we don't want to think about it as 3 pi over 2 to 2 pi and then 0 to pi over 2. We want to think about it as just negative pi over 2 to pi over 2, including those negative angles. Y equals sine inverse of square root of 2 over 2. So sine of y is equal to square root of 2 over 2 on the interval of negative pi over 2 to 2. So in between quadrants 4 and quadrants 1, sine is positive in quadrant 1. So, and we know that sine has that value of square root of 2 over 2 at pi over 4. Now, at this point, I encourage you to pause the video. We've got 4 more examples, but go ahead and pause the video and give it a shot on your own, and then come back and I will explain these 4 examples as well. Y equals sine inverse of negative square root of 2 over 2. So now we're trying to find sine of y equals negative square root of 2 over 2. Again, that value of y is on the interval from negative pi over 2 to pi over 2. So y is negative pi over 4. Y equals cosine inverse negative square root of 2 over 2, excuse me. So cosine of y equals negative square root of 2 over 2, and y is going to be on the interval from 0 to pi. So cosine's negative in that second quadrant, which is going to be 3 pi over 4. at this point, if we're not really familiar with the unit circle, these problems are going to take a little bit longer. So the more familiarity you have with it, the more you're practicing it, the less you're looking at it every single time. If we're really training our minds to try to remember or figure out these values, the easier this is going to become. If you're constantly having to look back at that unit circle, you're not forcing yourself to remember any of those patterns, which is, again, going to make this a little bit more challenging, or not necessarily challenging, but maybe a little more time consuming. Y equals arc cosine of negative square root of 3 over 2. So cosine of y is equal to negative square root of 3 over 2. Again, y is on the interval from 0 to pi. Here I like to think about those triangles. Cosine is equal to that negative square root of 3 over 2, which is the longer value. So if I think about sketching this triangle, I want a triangle in my second quadrant, but I want it to be sort of flatter, closer to that x-axis, so that I have my x value having a longer magnitude than my y value. And those flatter triangles, one closer to the x-axis, I know has a measure of 30 degrees. So to find, or pi over 6, so to figure out the angle measure, which is from my positive x-axis to that terminal side, is going to be 5 pi over 6. Or pi minus pi over 6. Y equals sine inverse of 2. So we're thinking sine of y equals 2. And here's where we need to know some properties about our trig functions. I think it's easier for me to remember the properties of our trig functions rather than the inverse. So I still like to rewrite it like this: sine of y is 2. And if I think about my graph of sine of x, or in this case y, it doesn't really matter what that variable is, I have a range from -1 to 1. So I'm never going to have an output for sine of an angle that's greater than +1. So this has no solution. Now, the other thing that you could think about is, what's the domain of inverse sine, which we did write on our summary on the previous page. The domain of sine was, or the domain of inverse sine was -1 to 1. So we can't even plug in a value of 2 into this inverse sine function because it's outside of the domain. Evaluate the following expressions. So the first one is arc cosine of sine of pi over 3. Thinking about the components of this particular expression. So we've got an inside function and an outside function. If we think about the outside function, arc cosine, we're not substituting in an angle, right? We plug in a function value into an inverse or an inverse trig function to figure out what the angle is. So this whole expression, because that outer function is arc cosine, is going to give me an angle measure. What we want to do is start from the inside and work our way out. So let's first find sine of pi over 3. Sine of pi over 3 is square root of 3 over 2. Now, depending on how you choose to remember that value is up to you. I still rely on my nice pretty triangles on my unit circle. Pi over 3 I know is that marker closer to my positive y-axis. So it creates a taller triangle. Because the triangle is taller, that means my y-coordinate is square root of 3 over 2. My x-coordinate is 1/2. So sine of pi over 3 is that y-coordinate, or square root of 3 over 2. Arc cosine of square root of 3 over 2. We're trying to evaluate this. So really what we're asking is cosine of what angle theta is the square root of 3 over 2. But remember, theta has to be between 0 and pi. So where does cosine have the values square root of 3 over 2? again, thinking about a positive cosine is going to be in my first quadrant. And I want that longer x side, so it gives me that flatter triangle closer to the x-axis, which is a angle measure pi over 6. Arc cosine of sine of 4 pi over 3. So again, starting with that inside function, sine of 4 pi over 3. So I'm going to sketch out my triangle, 4 pi over 3 if I count out multiples of pi over 3. Here's 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3 is going to be down here where that terminal side is closer to the negative y-axis. And now I can determine that that order pair is negative 1/2. Negative square root of 3 over 2. Because the horizontal leg is shorter than the vertical leg. So sine of 4 pi over 3, sine is that y coordinate, is negative square root of 3 over 2. And arc cosine of negative square root of 3 over 2, we're trying to find cosine of theta, that equals negative square root of 3 over 2 on the interval from 0 to pi. So I might sketch another triangle. Since cosine is negative, we're going to be in that second quadrant. And I want that horizontal leg to be longer. So that gives me that flatter triangle closer to the negative x-axis. And I know the angle between the negative x-axis and my terminal side is going to be that pi over 6, making our angle in standard form 5 pi over 6. Secant of sine inverse of negative 3 over 5. This one's a little bit different because now our outside function is just a normal trig function. So we're not going to be ending up with an angle measure. We have to figure out an angle measure here to plug into our secant function. Still working from the inside out though. So sine inverse of negative 3/5. We're going to call this theta. So my first step, I need to figure out what theta is. I know that sine of theta is equal to negative 3/5, and theta has to be in either quadrant 4 or quadrant 1. So from negative pi over 2 to pi over 2. So I'm going to draw my picture here because this output of 3/5, negative 3/5, is not something that's going to be on my unit circle. So I need to draw my triangle. Because sine is negative and I have to either be in quadrant 4 or quadrant 1, we're going to be in quadrant 4. Sine of theta is opposite over hypotenuse. So my opposite leg is going to be negative 3. My hypotenuse is going to be 5. And I can find that missing side by looking at, or by using the Pythagorean theorem. So 5 squared equals x squared plus negative 3 squared. 25 equals x squared plus 9. Subtracting 9 from both sides, x squared is 16. And because we're in the fourth quadrant, x is going to be positive, so x is positive 4. In a previous video, I did mention Pythagorean triples. If you're recalling some of these Pythagorean triples, you may not need to go through the work of using the Pythagorean theorem. But if they're not something that you have committed to memory, it's a real quick calculation using the Pythagorean theorem like we've been showing. So sine of theta, we've drawn our triangle to represent our angle theta. What we're really looking for in step 2 is what is secant of theta. Remember, we used sine inverse of -3/5 to represent theta, so we're really just trying to find secant of theta. And secant of theta is going to be the reciprocal of cosine of theta, so it's going to be your hypotenuse over the adjacent side. Which is equal to 5/4. Sine of 2 tangent inverse of 12/5. So we're going to work from the inside out. This tangent, inverse tangent of 12/5, this value is going to be our theta. So that first step will be to try to figure out some more information about theta. We know that tangent of theta is equal to 12/5. And theta's got to be in either quadrant 4 or quadrant 1. So from -π/2 to π/2. Since tangent's positive, that puts us in quadrant 1. And tangent gives the ratio of opposite over adjacent. So the vertical leg of this triangle is 12, the horizontal leg is 5. And then we can use the Pythagorean theorem to figure out the hypotenuse. I'm going to use r to represent the hypotenuse. So r squared equals 5 squared plus 12 squared. R squared equals 25 plus 144 or 169. If we take the square root of both sides, r is equal to 13. And that value of r is always going to be positive. So step 2, we are looking for sine of 2 theta. Here's where we bring back those double angle formulas we learned in a previous video. Sine of 2 theta is equal to 2 sine of theta times cosine of theta. From our triangle, we can see that sine of theta is 12/13. And cosine of theta is 5/13. Multiplying this across, 2 times 12 times 5 is 120. 13 times 13 is 169. I didn't check to see if that's simplified. Let me look. Nope, it does not simplify. So that's our final answer.